All right, welcome back to the next part in this video, which is going to focus on checks. So we're going to focus on when the king is in check and how to go about dealing with those invalid moves. Now I'm actually going to show you a naive solution that is pretty easy to implement, but does lack in efficiency. And then I'm going to show you a more complicated solution that that's going to be more efficient but much harder to implement. And I'm just going to show you that. So I'm just going to talk through that more complicated solution, but I'm going to actually implement with you the more naive, simpler solution. Okay, so where we left off last time, just to review, is we had our board now working where we could play all the different moves. And so we can now move the white and the black pieces, even the non pawns. We can move them, and it works pretty nicely. Let's see, and everything is good except for the fact that when the king is in check, such as in this example, we can make a move like that, which is not a valid move. You know, that's a valid move. That's not a valid move. So there's a few moves that are invalid, and so we need to find a way to deal with this. All right. So one of the things we're going to do very quickly here is we're going to just keep track of the location of the kings. The king is the most important piece from a logical perspective because it limits where pieces can move beyond the basic rules of the game. When a piece is pinned, and what we mean by that is when a piece is like, say, a bishop is attacking the king and you block it with a piece, you can't move that piece until the king makes a move. So what does that look like? Maybe something like this. So let's just say that we do something like this, and I move my bishop out to this square here. This pawn is now pinned because this bishop here is attacking the piece, the pawn right here. So this move should not be allowed because it allows the king to be under attack. And so we gotta think about a way to not only check to see if the king is under attack, but if a move leaves the king under attack. So what I suggest doing, and this is for a little bit of efficiency's sake, is let's actually keep track of the king's location. Kings always start on the same square, and when they move, we're going to keep track of where they move. And this will save us a little bit of time because we don't need to actually scan for where the king is and locate it if we just keep track of the king's location. So the king's location, we're going to have two variables to keep track of it. So the first one is going to be the white king location, and it's going to start at row 7, the back row for white pieces, column 4. And the black king location is going to start at row 0, column 4. We're just going to use tuples to keep track of them. It's a little of that extra data. And the benefit to doing something like this is it's also going to make checking for castling a little bit easier as well. We'll go into that later on. All right, so let's think about the logic behind generating now valid moves. So let's also, all right, while we're still on this king location, before we get into checks, let's actually update the king's location now when we make a move. So when we make a move or undo a move and it involves the king, let's just make sure that we update that king's location. So here, after we make a move, let's say move, but maybe before we, maybe before we, I guess it doesn't matter if we do it before or after we switch turns, but let's update the king's location if moved. And so we're going to check to see if the piece moved, which is stored in our move, is equal to the white king. Then let's update the white king location to be equal to the move end row, move end column, and same idea for if it is the black king that's moved. So else if the piece moved is the black king, then set the black king location equal to move end row, end column. So this just will update it. And in a similar fashion, when we undo the move, so we're going to put this inside of that undo move. Now, if the piece moved as the white king, now instead of moving it to the end row, we want to move it back to the start row, start column, and undoing the move. This is just a little quality of life thing that's going to help us out later. And you'll see where we use this later on. So add that in. That's a variable that we're going to keep track of. And anytime the king moves, we now update its position. Update king's position needed. All right. So we have that. That's looking good. Now let's talk about the logic for valid moves, because we kind of passed this up so far. We just said, let's just, for now, we're just not going to worry about checks. Let's just, every move is valid. And like I said at the beginning of this video, we're going to do a naive solution, and then we're going to do a more complicated solution. And so the naive solution is, I'm going to go through the algorithm here. It kind of starts with this idea that let's first generate all the moves. So let's kind of go through this algorithm. So let's generate all the possible moves, whether they're valid or not, in terms of leaving the king in check. Then after we have all the moves, let's make the move. So for each move, make the move. After we make the move, let's generate all opponents' moves. And then for each of those moves, for each of your opponent's moves, see if they attack your king. And if they do attack your king, it's not a valid move. All right. So we're actually going to be making a move and then undoing a move. And it's the reason we're doing it this way. This solution is pretty easy to implement. There's certainly another algorithm for this that's definitely more efficient. You can see right now the inefficiency already building up. Right now, basically, you're generating all of your moves. And then for each of those moves, you're generating all of your opponent's moves. And then checking to see if those opponent's moves can attack your king. And so you can see you're going to be generating tons of moves that you don't really need to consider most of the time. And so there is definitely a better way of doing this, but it's much more complicated. And so I just wanted to start with a very easy solution that we could implement pretty quickly. All right, so we already actually have this part. So actually, let's go ahead and get rid of the return statement here. Let's just return this variable moves. All right, so what is moves going to be equal to? Well, it's going to be all our possible moves. We've generated all the possible moves. Step one of our algorithm done. Now, for each move, make the move. Now, because I might be removing moves from this list, anytime you're removing elements from a list, you want to go through that list backwards. If you go through the list forwards with a for loop, what's going to happen is your variable I is going to go forwards incrementally. What ends up happening is, let's say I remove from the list. Let me just give you a list here to look at. So let's just say I have the numbers 0 to 5 here in this list, and I have a for loop that's going through these lists. You know, for num in nums. I'm just giving this really elementary example here. Actually, let me add in the number 3 twice here, just for the purpose of this example. For num and nums, let's say I'm trying to remove the number 3. If num equals 3, remove nums dot remove that number. Now you would think that this would work just fine, because it's going through here and it finds the number 3 and it removes that number 3. But one of the issues with incrementing through a list in this way is that you're actually iterating through it, and what can happen is you can remove this element 3 the first time you run it. And then basically what happens is it shifts all of the indexes of the remaining elements to the left. And so then your iterator will iterate to the next index and will actually skip over the other 3. And this can happen if you are not careful. So there's a bug that can happen if you're not careful. So my suggestion to you is anytime you are potentially removing things from a list or looking for things to remove from a list, you use the following rule, which is go through the list backwards. Start at the last element, go through the list backwards. Because then when you remove it and the indexes shift, so if I instead I start from the back here, and I start with 5 and I check that, and then I start with 4 and then I check that, and then I start with 3 and I see that and I remove it, and then I go to the next index down, it doesn't matter that these indexes shifted because I've already checked them. And so that's the benefit of going reverse. That's what we're going to do here. If you're wondering why I'm using this weird notation for this for loop, that is why. So here we start at the length of moves -1, which is the index of the last element. -1, -1. So my general rule of thumb is when you're removing from a list, go backwards through that list. You'll avoid a lot of bugs. Just remember that. That's something to remember all the time. Anytime you're dealing with a list, you're removing elements from the list while you're iterating through that list, start with the last element, go to the front. That's you won't mess up that way. You won't run into having errors that way. Okay, so for each move, now we're going through the moves. Let's go ahead and make the move. All right, make move. And what's my move? Well, it's going to be moves I. Okay, so now I have the move made, and I need to now generate all of my opponent's moves. The methods that are going to help us here are going to be one is going to be this method Incheck. And because the reason I want to do this is later on we're going to want to see if the player is in check anyway, to see if the game is over, for example. So I have to write these methods anyway, so I want to write them outside of the function get valid moves. I could easily write these functions right inside here, write the code that I'm going to write in here, write it in here, but this will allow us to use these methods in other situations as well, since they could potentially serve two purposes. And this is called something in programming called decoupling. We're basically taking this responsibility out from the valid moves function and putting it into another function itself called Incheck. Right? And so and then another helper function we're going to have is square under attack. And this is going to check to see if the square RC is under attack. Okay, so two things, these two functions. So this function here will determine if the current player is in check. And how do we do that? Well, we'll use this square under attack, and this will just take and it'll determine if the enemy can attack the square RC. So you can see how these two functions might work together. So Incheck is going to be simply this. If it's white's turn to move, then we are going to just return square under attack of the white king location. 0, white king location 1. So if it's white's turn to move, let's see if the square is under attack. If that square is under attack, that person's in check. Simple enough. And if it's black's turn to move, so else, basically the same idea. Let's see if the square under attack the black king is currently occupying is under attack. Now again, I could have easily put this this code, I could have put it up here, right? I could have done that, and made a call to that function, but I'm gonna put in its own method here. And then this square under attack function, what's going to go in here? This is the logic for seeing if R and C is under attack by an enemy piece. Now, I'm assuming that it's one person's turn right now. And so what I want to do is I want to switch to the other person's turn. So what I'm going to do is I'm going to just set self white to move equal to not self white to move. So I'm going to basically switch to my opponent's point of view. Because I want to see their moves. And this is when I'm going to go ahead and generate my opponent's moves. So here's where I'm going to actually take this line of code here. So I am generating all the opponent's moves, but it's going to be in another function. I'm still following my algorithm, but it's going to be doing it in this square under attack. So I switched to my opponent. I'm going to generate all the moves. And then I'm going to then go through those moves and see if any of those moves are attacking my square location. So for move in opponent's moves, if the move end row equals R and the move end column equals C, that's how I know if I'm attacking that square. The end row and the end column are on R and C. That means that square is under attack. So I want to make sure that I switch back turns before I return true. Otherwise, it will mess up my turn order. So this function can't modify the turn order. So I switch the turns. I'm going to switch the turns back. And then I'm going to return true because the square is under attack, which will mean that if it's white's turn to move, then I switch to black's turn to move. I generate black's moves. I check to see if any of those moves end on the king's location, the white king's location. So if any of black's moves end on the white king's location, switch it back to white's turn and return true. If none of those moves, I go through all the moves and I get to this end of this for loop, that means that square is not under attack. I still need to switch back turns. Still need to make sure switch back turns. And so I guess you could have, I guess we could put the switch turns back into here. That's maybe a better way of doing it because then we don't have it twice. So we'll put it before the for loop. And then I can return false. A little consolidation there. So I generate my opponent's moves, make sure I switch the turns back, then I go through all the moves and I return true if one of them ends on the row and column. Otherwise, I return false. That means that square is under attack, which also means that my Incheck method will now work. So how can I use this Incheck method now in the main bulk of my code? Well, let's go back up to our valid moves function. So in a sense, the Incheck function is generating all of my opponent's moves and checking to see if they attack your king. So steps 3 and 4 are actually done in another function here. And so I just need to call that function. So if self.incheck. Now, here's the thing. And this is where it gets a little bit it's a little bit tricky with the turns. When you make a move, it switches turns. Our make move function swaps the player. We have it do that. So I'm generating all of white's moves. Then I'm making one of the moves, which means that it's now black's turn. So if I do the Incheck, it's going to think that it's black's turn to move, and it's actually going to be looking at the black king's location. So before I call Incheck, I actually need to swap turns again. All right, hopefully that made sense. If that didn't make sense, go back through what I just explained there. Just watch the last like 30 seconds and listen to that again. We need to make sure that we switch the turns before we call Incheck, because make move switch the turns. Make move switch the turns. We switch the turn back. We check to see if now white is in check, so this will generate all of black's moves. Check to see if they're in, and it'll return true or false. If our king is still in check after we make that move, then we need to remove that move from the valid list of moves. That's not a valid move. So we say moves remove, moves I. And this is again why we're using the I notation here. All right, so I'm removing that move from my list. And that's this kind of step number 5 here. If they do attack your king, it's not a valid move. Now, if they don't attack your king, then it's a valid move. We should keep it there, but we still need to undo what our algorithm did. Our algorithm made a move, and it also switched the player's turn one time. So now we need to switch the player's turn back, and hopefully you understand why. Right? When we were checking in check, we wanted to see if white was in check. The person that just made a move was in check. So make move is switching the move. So there's a little bit of, again, this is why I said there's a little bit of inefficiency in this algorithm. We can see we're kind of switching variables back and forth here. And then we need to undo the move. And since undo move will also switch the turn, our parity will be good. We just want to make sure that the number of times we swap player's turn is even. Right? So here we make a move, it swaps the turn. That's the first time we swap the turn. Then we swap the turn again. So we're back to the first, whoever player's turn it is, we're back to their turn. And then in check, well, does that switch the player's turn? Not directly. Oh, I'm going too far down. But it does switch it here. But in this method, we just switch twice. So those are even. So those cancel each other out. And then this cancels out with this. And then make move cancels out with undo move. So we have all of these pieces working together to make sure that this works. Okay. So that should prevent us from making invalid moves now. I think that's it. Let's just go ahead and verify that. So let's test out our code. Let's do a couple moves here. Let's say we do this, and let's say we put our computer in check here. So king is now in check. So any move resulting in the king not being in check anymore should be valid, but moving the bishop there to c8 to e6 is not valid. Moving the bishop from c8 to d7 is fine. You can see it lets me do that move, but it won't let me move along another diagonal. It will let me move my pawn forward 1 square to block the check, but it won't let me move 2 squares to block the check. It will let me move my queen. And that's basically the only moves it'll allow. It'll move my knight, or I can move my knight here. So I'm basically, it's generating all the moves, but it's saying only these moves are valid because they block the check. All right. And so what happens whenever you get a checkmate? I'm just gonna do a really bad checkmate here. Let's just say that I shouldn't do that yet. Let's move whites here. All right. And then let's go ahead and that. All right. So this is now a checkmate because there's no moves that can capture the king, and the king can't move itself. The king can't capture the queen. So there's no valid moves, and so our game should end right now. And so the way I am going to do this is by adding a couple more fields here. So at the top here, we're going to add both a checkmate. We're going to assume that it's false, and a stalemate. We're going to assume that that's also false. So checkmate is when the king has no valid squares and it's in check. A stalemate is when the king has no valid, or there's no valid moves and the king is not in check. So both of these will come into play here. So after we get the valid moves, before we return them, what we're going to do here is we're just going to check to see if the length of valid moves is 0. Because this means that it's either checkmate or stalemate. There's no valid moves to be made, so it's either checkmate or stalemate. And how do we do this? Well, let's check to see if it's in check. And this is another reason why we wrote this as a separate method. So we can check to see if it's in check. And if it's in check, then we can say checkmate equals true. And if it's not in check, then stalemate equals true. All right, and if the length of moves is not either of those, then we'll set these back to false. This is just whenever we make moves and undo moves, if we make a move and it's checkmate and then we undo that move, checkmate and stalemate will still be true. So we want to make sure that we just update those. That's all that's for. We could probably put these in undo moves, checkmate and stalemate and undo move, and that would work as well. Anytime you undo a move, set checkmate and stalemate to false. We could just do it here as well. So there's a couple locations. But now we have a variable that will tell us when our game is over, which we can use in the main part of our engine. And we'll do some of that with the UI stuff in a little bit, and probably in the next video. So I'm just looking at some of my notes here. Let's see. So what I want to do still, I still want to do castling, en passant, and pawn promotion. 3 rules that are kind of different, involving check or involving chess. They're pawn promotions and en passant are 2 pawn moves that aren't our normal pawn moves, and then castling is a king move that's not really normal. And all of those 3 will require us to do a little bit more. Then I'll do some videos where we work on the UI a little bit. We'll add in highlighting, we'll add in some animations, possibly do flipping the board so we can see it from black's perspective as well as white's perspective. Maybe get into like making a little menu, something like that. And then finally, we'll wrap up this video series with some basic AI algorithms, which I'm excited for. All right. Thanks again. I will talk to you guys soon.